Alright, let's go with module 3 of the paper and then we'll move through it. Right? The industrial synthesis of ammonia, known as the Haber-Bosch process, is depicted in the figure below. Alright? Identify the species represented by the labels A, B, C, and D in figure 4. What would A be? What would B be? What would C be? Excuse me? Oh, you are right, my bad. What kind of. Okay, and then the. Look at that. And people say module 3 difficult. Come on now. B. Use an equation with state symbols to indicate the process that occurs in vessel E. Vessel E, I got have one nice is it iron molybdate something catalyst? Is either that or the iron catalyst? But let's look at this. We can use the iron catalyst. So what's happening in that? In E, so N2 gas, because it's a state symbols, plus 3 moles, because it's a 1 to 3 ratio of H2 gas, right? That would give us no 2 moles of NH3 gas. Oh, the reversible arrows. Okay, lovely. So I have that there. And this is the presence of an iron catalyst, right? At 4 450 degrees Celsius and 200 atmospheres. Okay, lovely. So we should have those responses. Use the chemical formula and state symbols to indicate the process that occurs in vessel F. What happens in vessel F? Really, really simple, right? Okay, go ahead. Somebody raise your hand. So, are you liquid to gaseous? Sure. What is this process? Is that L word? You know, the word is liquefaction, right? That's the process, liquefaction. Let me just put it here. Liquefaction. Lovely. Oh, my apologies. Because condensation implies that you don't have a God complex, which all chemists do. So we tend to use bigger words that look fancier. Every chemist have a God complex in some respects. Oh, look at that. The Chatelier's principle, as I was talking about this morning. The reaction to form the ammonia product is favored towards the formation of the product under certain reaction conditions. State the Chatelier's principle and use it to explain how increases in the pressure of the reactant support the formation of the ammonia product in the Haber-Bosch process. What is the Chatelier's principle? Okay. That response shows me that you understand. Mm-hmm. True. Hmm. So that's a lovely response, right? Everybody has their different ways of posing it, all right? As long as you understand the concept. Explanation now. What were we supposed to explain? Oh, increasing pressure. Okay, so stated before. Mm-hmm. So it's 4 moles on the product side and it's going to 2 moles. Lovely, right? And then that would now increase. Let's hope I can spell increase. Lovely. Ammonia yield. Also yield spell I before E. My bad. Lovely. All right. So looking at stuff like that. So you just need to give an actual explanation of it. Obviously, that one line that I put there is not the 4 marks. But you need to explain it, right? So speak about the Chatelet's principle with gas particles with increasing or decreasing pressure, and how we favor the least amount of moles when increasing pressure, and we favor the most amount of moles when decreasing pressure. Speak about those things. Explain to them. Let them know that you know what the Chatelet's principle means. All right. So, to identify the unique feature of the starting reactant that is most responsible for the exothermic nature of the reaction. Unit 1 chemistry okay. Alright, my bad. Go ahead. Anybody has a unit 1 response for this? Because I don't think this is a unit 2 chemistry. But anybody has a response. Identify the unique feature of the starting reactant that is most likely responsible for the exothermic nature of the reaction. What does exothermic reactions mean with respect to bond breaking and bond formation? Hello? Uh, well, yeah. Alright. But we're looking at the feature of the molecule, you know. Look at the feature. Mm-mm. Mm-mm. Yes, 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 yes. Lovely. Who is that? Oh my gosh. She just won. Wait, you just won props. Alright, lovely. So the end to end, I can't represent triple bond on this. Triple bond, right? Oh my gosh, BOND, right? Has a high bond energy. So you require a large amount, copious amount of energy, right, to break that bond in order to reform ammonia. And that is why we have an exothermic reaction here. That's why the reaction is exothermic in nature. Alright? And now we have to state the conditions for the reaction. We know it is 450 degrees Celsius, right? We know it is 200 atmospheres, and we know it is the presence of a iron catalyst. And we say module 3 difficult. Can't believe that. Let's move on. Indicate how each component of the conditions, right, stated in D3 increases the rate of collisions of reactant molecule. This is unit 1 again. Okay, I'm starting to get why the people were trying to like boycott this paper. Right? No, but yeah, but the thing isn't. Mhm. No, sir. The thing is, no. I understand why persons are gonna be upset. I think I'm answering the question without allowing anybody to go, but we have a small amount of time, right? But the thing is, no. I understand why persons are upset, but as a chemistry unit 2 said, you should know exactly what the answer is. To be very honest, whether or not it's like an assumption. Feel. Mm-hmm. I do know what you mean. For the first time I did chemistry, I got a two and went back from a distinction because the school didn't give him two. Um, all right, catalyst, lower activation energy. Okay, lovely. So we're looking at all of these conditions, right? So the pressure it increases collision frequency. We know the temperature increases kinetic energy. And we know the catalyst lowers the activation energy, and we must be able to explain these things, right? This is really simple. It's a basic chemistry, right? It's just that you won't expect it on a Unit 2 paper. Right? The Haber-Bosch process generates 2% of the world's carbon dioxide emissions and consumes 1% of the world's energy. Indicate two ways in which carbon dioxide is emitted as a byproduct of the Haber-Bosch process. So one way it can be produced, because remember that the Haber-Bosch process they require high temperatures, not true? So that means that we need to burn fossil fuels to get that energy. So fossil fuel combustion. Right, so we have fossil fuel combustion. We also do it for hydrogen production. So we can do it for H2 production, right? Or for TEM production, right? Another thing we could use energy for high pressure conditions. So we burn it for all of these things. And these things are not necessarily stated explicitly in the syllabus, but as we say, we have to kind of really use the common sense to figure it out, right? State the effects of the major limitations of the reaction in the Haber-Bosch process. Well, sorry, in if the reaction of the Haber-Bosch process is done at STP. So STP, what would STP imply? What does STP mean, guys? And what is standard temperature and pressure? Standard temperature is what? Excuse me? Well, hold on. Go ahead. Wait, hold on. What's happening? 0 Kelvin? 0 Kelvin, guys? Guys, hold on. Hold on. 0 Celsius? No, let me just explain to you why 0 Kelvin cannot be achieved. Right? It is physically, chemically, scientifically impossible to achieve 0 Kelvin. Impossible. Right? So let's just state that that cannot be the answer. Probably it's mix we mix up, right? Obviously, let me just give you the benefit of the doubt. It's mix we mix up a while ago. It's 0 Celsius we did mean to say. Right, and even if we say 0 Celsius, we still know say it wrong because it's 25 degrees Celsius. Right? So we're going to work with the 25 degrees Celsius, right? And we're also dealing with 1 atmosphere. Lovely. Right? So 25 degrees Celsius is how much Kelvin? Are you trying to calculate like Fahrenheit or go ahead? 287, 288, it's 298. No problem. What you say? I can't tolerate those things. No. Oh, sorry. Crazy stuff. Okay, lovely. So the thing is now we know that we're actually working with low temperature and low pressure, that is standard temperature and pressure. Now, judging by what we know should be the conditions for the Haber process, what would be the effect now? Right? So what would be the effects of the STP? What would be the limitations? Mm-hmm. 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 Lovely. So equilibrium will favor the reactants. Lovely. That's the first effect. The second effect would be what? Mm-hmm. So it's same thing as well. So not only we will have a low yield because it favors the reactant side, right? But because of the low temperature, we're going to have a slow rate. The truth. So we're going to have insufficient collisions from collision theory in module 2 of unit 1 chemistry. Right? Go ahead. Mm-hmm. You know, that's a very true. Um, that is very true. Alright, so we're saying that because it's exothermic, we'd prefer lower temperatures. Okay. So would effect 1 be wrong? So the major limitation, what the person was saying, is that because it is exothermic, right, you'd have a greater yield at lower temperatures. But note that the pressure is lower than the temperature in this case, right? So looking at this, right, the temperature is too low to overcome the activation energy barrier, right? That's how we got the kinetic limitation as it relates to the slow rate, right? But as it relates to the low yield of ammonia with the thermodynamic limitation here, right, the pressure kind of trumps the temperature here, right? So even though the lower temperatures would be preferred for exothermic reactions, right, it is because of the pressure, right? So that is the main thing that we're looking at here. So there are multiple factors affecting it, right? And because the pressure is so low, the overall equilibrium position would still be to the reactants. Whether or not it is 100% to the reactants or 40% to the reactants, that is inconsequential, right? You will still favor the reactants, all right? So completing this paper, almost done. Identify two ways in which ammonia affects the environment. Any two ways. Eutrophication. All right, lovely. So when we use the ammonia and the fertilizers, and then we have a heavy rain, etc., it runs off into water bodies. It can cause eutrophication. All right, lovely. Um, any other way? Mm-hmm. All right. Okay, so lovely. That is a good point, but it won't necessarily fly for this question, right? That is a good point as it relates to risks, right? Personal harm and stuff like that, handling it. So the risk you take. but it is an air pollutant, no so? It will it the nitrogen it can be oxidized. Yes, it is true. That is true. Soil degradation. Degradation. You'd have to explain the soil degradation there because it is used as a fertilizer. So how would it degrade the soil? You're gonna have to explain the soil degradation there. Yeah. Oh yeah, that is something as well. If you use too much fertilizers, what you're gonna have a boom in the growth of microorganisms and stuff like that, leading to competition. So it's kind of like eutrophication but on land. But you're gonna need to like explain that one. That's fine. What I think it was Divine or Anushka was saying. Oh my gosh, I think it was Anushka. Yeah. So stating about the photochemical smog, ammonia itself can be oxidized, right, through photooxidation in the atmosphere, right, and then that nitrogen now can now contribute to photochemical smog. So those two things, right, that you guys stated, the two last things are kind of like they're not wrong, but they're a bit more far fetched. So you're gonna need to like flesh it out. All right. I mean, you need to flesh out every response. Let's just state that. Flesh out every response. Don't give the markers. Go ahead. Yeah, I would state that. I wouldn't write an entire epilogue, but I wouldn't just write eutrophication, air pollutant, and then move on. I wouldn't do that. Remember, your responses must be in complete sentences, unless it says the list, right? I think it should be. I mean, in this case, the question just say to identify. So I guess one word could work, but I would always write in complete sentences unless it says explicitly the list. All right. But H, as a fertilizer, ammonia is generally used in the form of ammonium salt. State a reason for this. Go ahead. Mhm. All right, so it's less volatile, right? So it won't evaporate. It won't just, move away. So we want it to be embedded in the soil, only to be released upon activation with water, right? So with water, it will become dissolved ammonium, right, for the plant to take up when necessary, right? So that is important. So we use that ammonium salt like ammonium nitrate, all right? Lovely. Give the formula for one of the most commonly used salts. Wow, I just said ammonium nitrate. Right? Ammonium nitrate would be NH4. No so? NO3. Mhm. That is it. And that is the end of the paper.